Rodrigues. We are already live on YouTube.
Good morning, everyone. I'm going to be your host this morning. My name is Rodrigo, and in today's technical session, we'll have 5 papers. There are going to be 3 full papers on genome rearrangements, and we'll have 1 paper on classification of medical images, and 1 short paper on a scientometric analysis of bioinformatic stools. So I hope you enjoy these presentations, and let's welcome our first presenter. Who's going to be Klairton Lima. He's going to present his paper, Sorting by Reversals and Transpositions with Proportional Restriction, which was authored with Alexsandro Oliveira, André Rodrigues, Ulisses Dias, and Zanoni Dias. So welcome, Klairton. You can start. We'll have 20 minutes for the presentation, and then after that, we'll have 10 minutes of discussion.
Okay, I will share my screen right now. Okay, can you see my screen?
Yes, I can see it.
Okay, thank you. Hello, everyone. Good morning. My name is Klairton Brito, and today in this presentation, I will talk about the sorting by reversals and transposition with proportional restriction. So this is the agenda of this presentation. Initially, I will talk about the motivation of this work, and then I will introduce some definitions and concepts that we use to obtain the results for the problem. Then I will talk about the results that we obtain for the problems, and I will conclude the presentation showing the contributions and the possible investigations that can be performed in the future. So what motivates us to investigate this problem? Well, in the comparative genomics, usually we are looking for similarities and difference when we are comparing the genome of 2 or more organisms. And we know that during the evolution process, mutational events can affect the genome of the organisms. In particular, we have the genome rearrangement events, which are mutational events that can affect large portions of the genome. And one way to determine if 2 organisms are far or not from the point of view of the evolution is to estimate the rearrangement distance, which is the minimum number of rearrangement events used to transform a genome into another. And in order to transform a genome into another, first we need to determine a rearrangement model, which is a set of rearrangement events allowed to transform a genome into another. And in this work, we consider the reversal and the transposition events. And during the process of the evolution, we know that the rearrangement events can occur with distinct frequencies. And in the literature, we can find different approaches. And the main 2 are the unweighted approach. And in this case, we assume that the rearrangement events can occur with the same frequency, and the weighted approach. The weighted approach tries to simulate the different frequencies that the rearrangement events can occur, associating a cost for each type of rearrangement events. And the problem is still to transform a genome into another using the rearrangement events, but now minimizing the total cost. And the total cost is the sum of the cost of the rearrangement events used to transform a genome into another. And in the literature, we can find, considering the rearrangement events allowing the reversal and the transposition events, the costs 1 and 2 for the reversal and the transposition events, respectively, and also the costs 2 and 3 for the reversal and transposition events, respectively. And the reversal event cost tends to be cheaper in comparison with the transposition costs. But even using the weighted approach, we cannot guarantee that the cheaper event will be the most used to transform a genome into another. And for this reason, in this work, we are investigating the sorting by reversals and transposition with proportional restriction problem. And in this problem, we include an additional constraint regarding the minimum proportion between the number of reversals and the size of the rearrangement event sequence used to transform a genome to another. We consider in this study the case where we know the orientation of the genes and also the case where we don't know the orientation of the genes. And now I would like to introduce some definitions and important concepts. First of all, we need to know how to represent the genome. And this work, we represent the linear genome as a permutation. And given a linear genome, we map each gene or block of genes as an element of a permutation. And to indicate the orientation of the genes, we associate a plus or a minus signs for each element of the permutation, representing then the orientation of the genes. Since we are working with permutations, we assume that there is no duplicated genes in the genome. And in the case where we know the orientation of the genes, we have the signed case and we obtain a signed permutation. Otherwise, we have the unsigned case and the map we obtain an unsigned permutation. Here in this illustration, we have the mapping process. We have two genomes. The first one is G1, or is the source genome, and the target genome is G2. And the oriented blocks indicate the genes with their respective orientations. To simplify the mapping process, we use a standard permutation to map the target genome. So the genome G2, as you can see, we have the elements of the permutations in an increasing order and with all the elements with positive sign. And we map the value of the source permutation according with the numbers that we have in the target permutation. Besides, if the orientation of the block is the opposite that we have in the target genome, we assign a minus sign to the element. For instance, in the genome G1, in the permutation, and the elements 5 and 3, we have a negative sign for these elements because the orientation is the opposite that we have in the target genome. So talking now about the sorting problem, when we map the genome as a permutation, as I mentioned before, we tend to assign a specific permutation to the target genome, and this permutation is called identity permutation. And for the unsigned case, the identity permutation have the elements within the increasing order from 1 up to n. And for the signed case, the identity permutation also have the elements in an increasing order and with all the elements with positive sign. And the problem when the genome is mapped into a permutation tend to be treated as a sorting problem for this reason, to simplify the process. And also, the identity permutation can be easily computed just with information about the size of the source genome. And then, an instance of our problem consists of just two elements. The first one is a permutation pi, which represents the source genome, and a proportion k, which is a value greater or equals than 0 and less or equals than 1. And the goal of the problem is to find a sorted sequence with minimum size capable to transform the source permutation to the target permutation, such that the number of reversals in the sequence S divided by the size of the sequence S is a value greater or equals than k. So now I will talk about the rearrangement events. The first one is the reversal events. Reversal is an operation Rho-ij, which inverts a segment of the genomes. And besides, if we are dealing with the signed permutation, the sign of the elements is swapped in the affected segment. As you can see here in this general example, we have the permutation pi, and below we are applying a reversal Rho-ij. As we can see, the affected genome have a line below. The segment is inverted, and also the sign of the elements inside of the segment is swapped. In the following example, we have the signed case example. On the top, we have the source permutation, and below we have the target permutation, which is the identity permutation, and a sequence of 3 consecutive reversals is capable to transform the source permutation into the target permutation. The first 2 reversals are applying just one element, as we can see. The first reversal is applying the element +2, and we obtain the element -2. And the second reversal is applying the element +4, and we obtain the element -4. And the last reversal is applying a block with 4 elements, inverting the segment and also swapping the sign of the elements of the affected segment. A transposition is an operation denoted by tau ijk, which exchange position of 2 consecutive segments of the genome. This operation does not affect the orientation of the genes. As you can see here in this general example, on the top we have the permutation pi, and below we are applying the transposition tau ijk. As you can see, the 2 affected segments, consecutive segments, they exchange position, but the orientation of the elements of the permutation is still the same. So considering now the signed case, we have an example with a sequence of 3 consecutive transposition in order to obtain the identity permutation. The first transposition is applied in the 2 consecutive segments with 2 elements each, and then followed by 2 consecutive transposition, just exchanging 2 consecutive elements. Note that the orientation of the elements is still the same, and none of the elements change their orientation. So, as I mentioned before, even using the weighted approach, we cannot guarantee that the cheaper event will be the most used in a solution that transforms a genome to another. In this example here, we have a permutation pi, and considering the costs 2 and 3 for the reversal and the transposition events, this is an optimal solution. Note that the sorting sequence is composed by 2 reversals and 2 transpositions, even using a cheaper cost for the reversal events. But now, if you use the same permutation and considering the proportion approach and using a proportion with value 0.6, which means at least 60% of the sorting sequence composed by reversals, we have this following optimal solution. Note that the sort sequence increases just by 1 operation, but now we have 4 reversal operations in the sort sequence and just 1 transposition. That fits with the proportion constraint in the problem. Now I would like to explain some concepts. The first one is the breakpoints. So the breakpoints are computed using the extended permutation, and the extended permutation, we include 2 new elements in the permutation. In the beginning of the permutation, we include the element pi0 with value 0. And the end of the permutation, we include the element pi n plus 1 with value n plus 1. And we have a breakpoint between 2 consecutive elements, pi I and pi I plus 1, if the absolute value of pi I plus 1 minus pi I is different from 0. Which means that the elements are not consecutive with the identity permutation, even in an opposite order. The total number of breakpoints in a permutation pi is denoted by B of pi, and the only permutation which has no breakpoints is the identity permutation. Here we have an example. On the top, we have the permutation pi, and below, and pi prime, we extend the permutation including the element 0 in the beginning and the element 6 in the ending. And then we have the regions where we have breakpoints with the stars, and the total number of breakpoints in this example is of the permutation pi is 4. Another important concept is the concept of cycle graph. So the cycle graph is constructed from an extended sided permutation, and the cycle graph is composed by a set of vertices and edges. The set of vertices is composed by, for each element pi I of the original permutation, we have the vertices minus pi I and plus pi I, and also we have the vertex plus pi 0 and minus pi n plus 1. The set of edges, we have black edges and gray edges. The black edges correspond to the adjacencies that we have in the source permutation, and the gray edges correspond with the adjacencies that we have in the target permutation, which is the identity permutation. Each vertex in this graph has degree 2 with 1 black edge and 1 gray edge. So it's always possible to find a cycle decomposition with alternating edge colors. And the total number of cycles in this graph is denoted by C of pi. And the only permutation which generates a cycle graph with n plus 1 cycle is the identity permutation. So here we have an example of the cycle graph constructed using the permutation pi with values +5, +2, +4, +3, +1, +6, and -7. And in this work, we draw the graph using the vertex in a horizontal line according with they appear in the source permutation. The black edges in a horizontal line and the gray edges forming an arc over the vertices. And in this cycle graph, we have a total of 3 cycles distincted by the colors black, blue, and red. So using the concept of the breakpoint and the cycle graph X structure, we can obtain lower bound for the problem. Considering the unsigned case, we have the lower bound, which is the total number of breakpoints divided by 3 minus k. And considering the signed case, we have the lower bound, which is n+1 minus total number of cycles divided by 2 minus k. And now let's talk about some of the results. Initially, I would like to show an overview about the complexity of the problem considering the different proportions. Considering the unsigned case, when the value of k is 0, we have the sorting by reversals and transposition problems on unsigned permutation, which is an NP-hard problem. And when the value of k is 1, we have the sorting by reversals problem on unsigned permutation, which is also an NP-hard problem. And when the value of k is greater than 0 and less than 1, the complexity of the problem remains open. Considering now the signed case, when the value of k is 0, we have the sorting by reversals and transpositions problem on signed permutation, which is an NP-hard problem. But when the value of k is 1, we have the sorting by reversals problem on signed permutation. And for this problem, we have a polynomial time algorithm. And similar with the unsigned case, when the value of k is greater than 0 and less than 1, the complexity of the problem remains open. And talking now about the algorithms that we proposed for the problem, the behavior of the algorithm consists for the unsigned case in remove, on average, a minimum number of breakpoints after apply a sequence of operations. Always keep the minimum proportion desired for the instance. And for the signed case, we use a similar strategy, but considering the cycle graph, in order to increase the number of the cycles after apply a sequence of operation, also keeping the minimum proportion desired for the instance. Since the identity permutation is the only one with no breakpoints and the only one which generates a cycle graph with n+1 cycles, eventually we will reach the identity permutation, which is the target genome. So we proved that for the unsigned case, the algorithm guarantees an approximation factor for any desired proportion with a constant factor of 3 minus k. And also for the signed case, the approximation factor of the algorithm guarantees an approximation of 3 minus 3k divided by 2. And also we showed how to obtain an improved asymptotic algorithm with approximation factor of 2k divided by 1 minus k divided by 3. So to conclude this presentation, I would like to show the contributions that we have done in this work. We investigated the sorting by reversals and transposition with proportional restriction problem on permutations. We incorporate into the model an additional constraint regarding the minimum proportion between the number of reversals and the size of the sorting sequence. This approach generalizes the unweighted approach and can be used considering the different frequencies that the rearrangement events can affect the genome, considering the rearrangements of reversals and transposition, just by adjusting the parameter k. And in this study, we considered the unsigned and the signed case. For both cases, we presented an approximation algorithm with a constant approximation factor. And besides, for the signed case, we showed how to obtain an improved asymptotic approximation algorithm. Considering now the works that can be performed in the future, we intend to perform experimental tests to compare the practical results of the proposed algorithms in this work with the theoretical results. It's important to simulate the different proportion scenarios in order to check the behavior of the algorithms in these different scenarios. It's also important to compare the algorithms with another algorithm in the literature, but it's important to create a way to provide a fair comparison between them, since the another algorithms do not have the constraint about the minimum proportion. Another important point is to investigate the complexity of the problem considering the proportion when the value of k is greater than 0 and less than 1. And at last, it should be interesting incorporating to rearrangement model non-conservative events like insertion and deletion. But probably in this case, it will be necessary to create a new proportion constraint in order to guarantee that it's possible obtaining a feasible solution that not use unnecessary operations. So I finish here my presentation. Thank you very much for your attention. If you have any questions, please let me know.
Thank you very much, Klairton. It's always nice to see someone working on these genome rearrangement problems, mainly involving the transpositions, which is a hard problem. So yeah, it's congratulations. It's transpositions are not only hard, but they're hard to prove they're hard. So it's
thank you.
It's a really hard problem. So so the microphone is now open for the audience to send their questions. So you can use the chat, or you can raise your hand to send us a question. So there's a question on the chat here from Georgie Cucci. Thank you for the presentation, and he says, in your work, you have considered only the DNA coding region, right? That's correct, right? Yeah.
Yeah.
So is it possible to consider the whole genome coding and non-coding region in the approach? Do you have any plans to address it?
Yeah, I mean, yeah, it is possible to incorporate this information to the model. Probably it will be necessary to change something about the modeling process, but yeah, it's possible, and it actually is a good idea. And actually, we have planned to extend this work and mainly showing the experimental test for this case and actually investigating the complexity of the problem. But yeah, this is a good idea to extend this work considering the non-coding regions. Yeah, it's a great idea. And thank you for your question.
So any other questions? So I do have one question. Yeah, the extremal cases, like with k equals 0 or k equals 1, there, most of them are hard, NP hard. So there's only the case of the sign permutations with a k equals 1, yeah, which is sorry, k equals 1, which is there's the famous Henry-Hahn-Metzner algorithm for sorting them. What is your hunch for the non-extremal cases? Like, do you think it's going to be NP hard? Do you have any hopes for a polynomial algorithm?
I mean, it's interesting, right? Because in the unsigned case, in both extremities, we have NP hard problems because the problem generalizes both. But for the signed case, in one extremity, we have the problem is NP hard. But when k is 1, we have the problem is in P. But it's quite complicated. But I guess that probably the unsigned case, the problem when the value of k is greater than 0 and less than 1, probably we can find that the problem is NP hard. But for the signed case, it's quite complicated and tricky, but it's interesting actually. So
yeah. And for the approximation algorithms, again, for the extremal cases with k equals 0 and k equals 1, we do have approximation algorithms with approximation factors they seem to be way smaller than the factors that you found here with 3 minus k, 3 minus 3k over 2, and 2 minus k over 1 minus k over 3. Those are for standard permutation. So it looks like these it's obviously a
maybe it's possible to improve the approximation factors.
Yeah.
I mean, for the signed case, when k is 1, you have a polynomial time, you have exact polynomial time algorithm. But for the unsigned case, the approximation range from 2 up to 3, and maybe using another strategy or another structure, maybe can be possible to improve this approximation factor. But maybe it will be a little bit complicated to improve initially, but yeah, we can try to improve the approximation factor, maybe to a value close to that we have for the unweighted approach, for instance. But yeah, maybe it's possible.
All right. Do you have any other questions from the audience? So if we don't have any other questions, Klairton, we thank you again. And on behalf of the audience, we thank you for your work, which is it's a great work, and I hope you have success in further developing this line of research.
Thank you very much. Thank you for your attention. And I will stop sharing my screen right now.
Thank you. So we're right on time for our next paper. The next paper is going to be presenting. Is it going to be Pedro Olímpio? Pedro, are you there?
Hello, I'm here.
Okay, so our next paper, still on genome rearrangements, it's going to be presented by Pedro Olímpio on the heuristics for breakpoint graph decomposition with applications to genome rearrangement problems, authored with Alexsandro Oliveira, André Rodrigues Oliveira, Cid Carvalho de Souza, and Zanoni Diaz. So welcome, Pedro. You can start sharing your screen.
Okay. Can you all see my screen?
Yeah, it's visible now. Mm-hmm. So we'll have 20 minutes for your 20-ish minutes for your presentation and 10 minutes for the discussion.
Okay, thank you. Good morning, I'm Pedro Pinheiro, and I'm gonna present the work Heuristics for Breakpoint Graph Decompositions with application in genome rearrangement problems. First, I introduce a little bit of the problem. The rearrangement distance between two genomes is a problem in comparative genomics that aims to find a minimum sequence of rearrangements required to transform one genome into the other. These genomes in this problem are generally represented as permutations, where each element of the permutations represents a gene of the genome. When the orientation of the gene is known, we use the minus or the plus sign on the permutations to represent this orientation. In this case, we say that this permutation is a signed permutation. Otherwise, we say that is an unsigned permutation. Since we can model one of the genomes as the identity permutation, the problem of transforming one genome into the another by rearrangement is equivalent to that of sorting permutations by rearrangement. That is, we just need to sort the another permutations to sorted in a ascending order to transform one permutation into the another. The most studied rearrangement models are the reversal, transposition, and the double cut and join operations. The problem of sorting by this reversal is NP-hard on unsigned permutations. In this work, we proposed a grid algorithm and an algorithm based on the Taboo Search meta-heuristics for the breakpoint graph decomposition, which is a problem with strong applications on the sorting by rearrangement problem. We also analyzed the performance of these algorithms in practice and compared them with the approximation algorithm proposed by Lin and Zhang. We also present experimental results of these algorithms applied to the genome rearrangement distance, considering both a model with these double cuts and joins and a model with reversal and transposition rearrangements. So now I will introduce some of the concepts I'm gonna use on this presentation. The first concept is the permutation, which I will call pi, where is a permutations of the first n positive integers. We call then on the order pi1, pi2 up to the pi n. And in this work, I'm gonna use extended permutation where we add a element on the beginning of the permutation, pi 0, that is 0, and the element on the ending of the permutation, pi n plus 1, that is the element n plus 1. The identity permutation, iota n, is a permutation where the elements are sorted in ascending order, like this, in this case, 1, 2, up to n. Two elements that are consecutive on the permutation pi makes a breakpoint if they are not consecutive in the identity permutation. That is if an element pi I and the element pi I plus 1, the absolute of their difference are bigger than 1, they form a breakpoint on the permutation pi. We also say that the number of breakpoints in a permutation pi is B of pi. So now I introduce the concept of breakpoint graph, which is a graph where the vertices of this graph are the elements of the permutation, and the edge sets are defined by the breakpoints of the permutation. For example, if if two elements are consecutive on the permutation, but must not be consecutive on the identity permutation, they have a black edge connecting them on the breakpoint graph. For example, the elements 0 and 6 of this permutation pi are consecutive, but not consecutive in the identity. So exists a black edge connecting them. The same goes to 6, 4, and so on. And if two elements are consecutive in the identity permutation and not consecutive on the permutation pi, they will have a gray edge connecting them on the breakpoint graph. For example, the elements 0 and 1 must be consecutive on the identity but are not on this graph, then exists a gray edge connecting them. In this presentation, I will always show the graph with black edge drawing this horizontal line, and the gray edges draw as arcs connecting two vertices. And finally, the alternating cycle is a cycle on the graph where consecutive edges have different colors. For example, the cycle 7106 is an alternating cycle because the edge 171 is a black edge, the edge 10 is a gray edge, the edge 06 is another black edge, and the edge 67 is a gray edge. The same goes to there's another example, H237. So now we arrive on the breakpoint graph decomposition problem, which consists, this problem consists in finding a set of edge disjoint alternating cycle with maximum cardinality. That is, we must decompose the edge set of our graph in alternating cycles that do not share an edge in a way of maximizing maximizing the number of cycles. In this example, we have two solutions. In this first solution, considering each color as the edges of each color as a different cycle, we have a solution with 3 cycles. In this other example, we have a solution with 4 cycles, which is optimal for this graph. So we proposed heuristics for the breakpoint graph decomposition problem. The first heuristic is a grid algorithm, which have 4 variations. The variations first, random, max, and all. On this algorithm, we use a BFS algorithm to find the shortest cycle, the shortest alternating cycle, which contains a given vertex. The difference between these variations is how this choose this given vertex to find the shortest cycle. By itself, the grid algorithm has no approximation factor, but we can adapt this algorithm to have the same approximation factor than the same approximation factor of the approach, the algorithm proposed by Lin and Zhang. We first need to solve the problem using the approach, then get all the cycles with less than 4, all the alternating cycles with less than 4 black edges, and then use the cycles on our grid algorithms. That way, the approximation factor will remain on the algorithm, the grid algorithm. And the other algorithm we proposed, other heuristic we proposed on this work is a taboo search based algorithm. I will explain it later. The first grid algorithm is the variation first, which has time complex O of n squared, and the vertex choose to find the minimum cycle is the leftmost vertex that still have any incident left edge. Then after we find this minimum cycle that contains this vertex, we add the cycle to the solution and remove the edges from the solution. And this example, after finding a cycle that contains the vertex 0, we have removed all these edges from the graph and repeat the procedure until there is no edge left on the graph. For this example, it will be able to find the optimal solution for this graph, which is a solution with 4 cycles. The second variation is the random variation, where the vertex is chosen randomly between all the vertex which have at least one incident edge left. For this example, if the first choose vertex is the vertex 6, then we find the red cycle. Then if the choose vertex is the 1, the blue cycle would be found. And finally, the green cycle would be the only cycle left on the graph. Then the solution returned will be the solution with 3 cycles. That is not optimum for this problem. As this is a non-deterministic algorithm, running this procedure several times can yield different results. So we proposed another variation called max that consists of running the random variation and square root of n times. So the time complexity of the max variation goes O of n cubed times square root of n. And the last variation of the grid algorithm is the variation all, where the minimum cycle is found by each vertex, by all the vertex that still has any incident edge. So the the minimum cycle of the graph is always found. For this example, it will find a solution with 4 vertices, 4 cycles. So let's move on to our other proposed heuristic, that is a taboo search based. For that heuristic, it's necessary to give a initial feasible solution to perform a local search trying to improve the solution, this given solution. For that, we propose 2 movements: the improving movement and a non-improving movement. This non-improving movement is necessary to the algorithm because they allows the search to keep running even after find a local optimum solution. The time complexity for this heuristic is O of n to the 4th. So I will now explain how the first movement, that is the movement who improves the solution, works. Given to this movement be applied, it's necessary having 2 cycles that share at least 3 vertices. In the example, the vertices U, V, and W are shared by this blue cycle and this green cycle. Then the paths between these vertices are also need to fulfill some conditions. If these conditions are fulfilled, we can replace the 2 vertices of the 2 cycles of the initial solution by 3 other cycles, improving the solution, the number of cycles of the solution by 1. And in the second movement, we have similar conditions. We need to have 2 cycles, but sharing vertex. But in this case, we just need to share 2 vertices, and the conditions for the path remains. And we replace the 2 cycles of the previous solutions for another 2 cycles. That can be useful if the first movement could not be applied on the previous solution. So we change the graph to attempt to apply the first movement in future iterations of the algorithm. We need to apply this movement carefully, because if applying this movement several times in a row can result in a solution already found by the algorithm in previous iterations. For example, this cycle, the same way that these 2 cycles can turn into these 2 cycles can be turned again on the first solution. So we keep a taboo list of forbidden movements for some iterations to prevent this to happen. So given these heuristics, we implement the Lin-Jiang algorithm, and both heuristics presented to analyze their performance. To compare them, we generated a set of permutations. Each permutation has the maximum number of breakpoints, and the size goes from 10 to 100 in intervals of 10, with 100 permutations of each size. And we performed 4 different experiments. The first one, we comparing the different versions of the grid algorithm against the algorithm of Lin and Jiang. The second one, we do similar thing, but we indicate to the grid algorithm that it must contain the same short cycles as the Lin-Jiang algorithms. The third experiment consists in running the taboo search on the top of the first experiment, including the Lin-Jiang's algorithm, and the fourth experiment consists in running the taboo search on the top of the second experiment. This table shows the average number of cycles returned in the experiments 1 and 2. On the experiment 1, the number of cycles returned in average of all the grid algorithms were way better than the number of cycles returned by the Lin-Jiang's algorithms, except for instances of small sizes like 10 and 20. But for sizes bigger than 20, in average, the grid algorithms always perform better. And among those algorithms, the one with better results is the max variation, which goes better than the Lin-Jiang's algorithm, even for instances of size 20 in average. For the experiment 2, the results are similar. The grid algorithm always goes better than the Lin-Jiang's algorithms for instance of size 20 or bigger, tie when this in instance of size 10 on average. And again, the max variation is the variation with better results. But we can note that when we force using the small cycles of Lin-Jiang's algorithm, the max algorithm has a worse performance than when it's not forced to use the short cycles, as you can see comparing this column of the table with this column of the table, that for sizes to 20 to 80, the results are worse. On this other table, we show the average number of cycles returned in experiments 3 and 4. That is the experiments where the Taboo Search are running in the top of the grid algorithms of the Lin-Jiang's algorithm. The results on the experiment 3 are very similar to the results of experiments 1 and 2, where all the grid algorithms followed by the Taboo Search yield better results than the results presented by Lin-Jiang's followed by the Taboo Search, and max continues being the better one among those. For the fourth experiment, the results remain where the presented approaches were better than the Lin-Jiang approach, and again, forcing to use the short cycles of Lin-Jiang have make the max variation yield the worst results than when it's not forced to use the short cycles. So the results in average with the variation with better number of cycles in average at the max variation of experiment 3, that is the grid followed by Taboo Search, the grid algorithm with max variation followed by the Taboo Search algorithm. And we also performed another experiment, because as the algorithms for breakpoint graph decompositions problem are often used as part of the approximation algorithms for genome rearrangement problems considering consanguine permutation, we used our algorithms as part of the approximation algorithms for the genome rearrangement distance. We considered two models. The first model uses the double cut join rearrangement, and for permutation pi and decomposition age, the length of the sorting sequence is equal to the number of breakpoints of the permutation minus the size of the decomposition. And the second model we used is a model where uses the reversal and transpositions rearrangements to sort the permutation, and that we have a lower bound and the upper bound for the size of the sorting sequence. The lower bound is the number of breakpoints of the graph minus the size of the permutation, the size of the decomposition divided by 2, and the upper bound is just the number of breakpoints in the graph minus the size of the decomposition. On this table, we show there is the average number of the average length of the sorting sequence. Note that for this problem, the objective function is minimization. So a result with less with smaller sorting sequences are the better results. The results for this table are very similar to the results of the previous tables, except for the first and all algorithms, where on the previous table the all variation yielded better results, and here the first yield. No, wait. Okay, then we the grid algorithms always continues going better than the Lin-Young's algorithm, and the better one continues being the max variation. And for conclusion, we studied the problem of breakpoint graph decomposition. We developed a greedy algorithm and the algorithm based on the Taboo Search meta-heuristic. The proposed algorithms yielded better results than the algorithm proposed by Lin and Young. The Taboo Search algorithm was able to improve the solutions returned by all variations of the grid algorithms and the results returned by Lin-Young's algorithm. And we also evaluated the solutions in our experiment using then algorithms for the rearrangement distance that receives a decomposition of the breakpoint graph as input. As before, the performance of our algorithms was significantly better than that of the approximation algorithm of Lin and Young. As future works, we intended to develop algorithms based on grasp and genetic algorithms meta-heuristics. This work was supported by the institutions CNPq, CAPES, and FAPESP. This was the reference used in this presentation, and this ends my presentation.
So thank you, Pedro, for your wonderful presentation on such a hard problem. We now open the microphone for the audience's comments and questions. So you may post your questions in the chat or raise your hand to voice your question. I'd like to compliment you on working on such a hard problem, which is it's been a while since he hasn't been working on it. So it's there's the Lin and Young's algorithm in 14 years ago, and before that there was the Alberto Pereira analysis on the using the cycle decomposition to prove that the sorting by reversals without signs was an NP-hard problem. So it's also an NP-hard problem. In your results, you show the average number of cycles returned by the experiment. Can you go back to the slide?
The average number of cycles is those two tables.
Yeah. So which is impressive because it's you almost double the cycles when compared to the approximation algorithm. What is the approximation factor of the algorithm?
It
the Young's algorithm.
Approximately 1.41.
1.41. So yeah,
yes.
those are very impressive results. Do you have any error bars on those results? Like because you see here, we see here like for the experiment 1, the max algorithm returned like 22 cycles on average, 22.17. But do the number of cycles, does it vary too much? What's do you know the variance of those on that number?
Actually, they do not diverge very much of this average, but I don't know right now the variation.
Okay, yeah, that was something nice to know. And something else that's nice. Does your algorithms, they always return results that are either equal or better than the linear Young's algorithm? Because well, there are heuristics, so it's not guaranteed, but in practice, is it like 100% of the results are better, or something like 90%?
For big instance is always better. It sometimes are worse when considering small instance. For this example, for example of instance of time of size 20, the Lin-Young's algorithm returned on average 6.558 cycles, and the other variations return cycles with solutions with less cycles on average. But when increasing the size of the instance, it always gets better. It gets 100% on big instance. Yes, it gets.
All right. Yeah. So yeah, that's but yeah, for large permutations, that's a very good result. So do you plan on publishing the code that you use to find those results? Because we usually don't publish code because that's just an artifact used to find the results. But yeah.
Yeah, this algorithm will be. I will publish these algorithms later on some site for. I will let them open.
Yeah. So just a suggestion, if you're looking for a venue to publish them, that there's an online journal called the JOSS, the Journal of Open Source Software, where you can have your code reviewed and they check if anyone else can build your code and reuse your code. So it's a nice place for those artifacts to publish those artifacts. So it's just a small suggestion if you'd like to consider that.
Okay, thank you. I'm gonna see.
And I'd like to thank you again for the great paper with great results, and wish you good luck in your endeavors.
Thank you again. Thank you all very much.
So for our next presentation, and this morning we're going to have is it João Meidanis? Are you there?
Yes, I'm here. Can you hear me?
Yes, we can hear you clear. So today João Meidanis is going to present to you his work with Priscila Biller, João Paulo Zanetti on the center genome with respect to the rank distance. So João, you can start sharing your presentation right now.
Okay. Thank you. Can you see my screen?
Yes, it's visible.
All right, so I'm here to talk to you about the center genome with respect to the rank distance. And this is joint work with Priscila Biller, João Paulo Zanetti. And we belong to a bunch of institutions, and the main sponsors of this work were FAPESP and the Simon Fraser University. All right, so the applications of our work are in inferring ancestors in a phylogenetic tree. So here you have an example of a phylogenetic tree. The internal nodes represent ancestors, and the leaves represent known genomes. And we want to reconstruct the genomes of the ancestors. One way of doing that is by using the median genome, okay? So the median genome, M, is a genome that minimizes the sum of the evolutionary distance against 3 others given as input. So starting with any, you can start with random genomes in all the ancestors, but then you refine your tree by successively choosing one node and replacing what's there by a median of its 3 neighbors, if the median is indeed an improvement. And if you keep doing that until you reach convergency, you can find a reasonable tree, okay, with reasonable genomes in all the ancestral nodes. However, perhaps the medians are not the best tools for that. For one thing, when you have 2 genomes and you think of a median of 2 genomes, a genome that minimizes the sum of the distances to the extremes, you can see that you have a lot of medians, and most of them are not very representative of what you want, because including the extremes, A and C are medians as well, and some of them may be much closer to one or to the other. So they're not very good as medians. For 3 genomes, you have a suitable representative, but to find the median for 3 genomes is NP hard for many rearrangement distances, even simpler ones like the reversal distance, or the more popular ones, such as the DCJ. In contrast, if you are willing to use centered genomes, you have maybe a couple of advantages. One being that even for 2 genomes, the centered genome problem can produce more relevant solutions because it's more constrained. So not every genome between A and C, or in an optimal path between A and C, is a centered genome. You have to pick one that's right in the middle or close to the middle if you have 2 equally positioned middle genomes. So you have much more constrained solutions for 2 genomes. For 3 genomes, we don't know the complexity of the centered genome problem. It may be NP hard as well, just like the median, but it's open. All right, so another advantage of using the center of 2 genomes is that if you use the successive median computation to improve the genomes in the tree, you don't know exactly how many steps you're going to take, because you may have to revisit nodes after the neighbors have been updated and so on. But if you use centered genomes, then you can visit each ancestral node only once in a bottom-up fashion, and be done with it in at most n steps. All right, but which evolutionary distance are we using here? We are using the rank distance. The rank distance between 2 matrices is defined as just the rank of the difference of the matrices, okay? It has been very successfully used in coding theory for many decades now. But we also want to make a point that this rank distance is very useful for genomes. Yes, 4 genomes. The thing that you have to do is to represent genomes as 0-1 matrices. And here's an example. So take a genome. In this case, we took a circular genome with just 1 chromosome and name the extremities. Okay, mind that. We're not naming the genes. We are naming the extremities of the genes. So here we have 2 genes and 4 extremities. And the extremities will correspond to the rows and columns of the matrix. And then the matrix is all zeros except for ones marking the adjacencies, okay? Extremities of genes that are consecutive to one another in the genome. So in this example, A and C, you have one denoting this adjacency, A and C, and another one is B and D. You also have one marking this correspondence. So you always have a symmetric matrix, all right? If you have linear chromosomes, it's the same, except that for those extremities that are not linked to any other, each linear chromosome will have 2 of those in the far right and far left, say, in our case, D and B. Okay, for those extremities, you just plug in 1 in the diagonal, okay? So that's how you represent the free ends. And, okay, so if you represent genomes like that, then when you compute the rank distance, see what happens. In every place that the genomes agree in an adjacency, the columns become 0, the rows become 0, and they don't contribute anything to the rank. The rank will only be affected by adjacencies that are different in both genomes. So this means the usual rearrangement operations like reversal, transposition, and things like that, that only affect a few extremities will lead to a rank distance very small. Okay, so for instance, let's think of 2 or 3 very representative genome operations that you can see a lot in evolution. The join of 2 adjacencies and its inverse, the cut of an adjacency. Okay, so that's a link in the genome that's broken or reenacted. And then you have the double swap, where you have 4 extremities involved in pairs, 2 by 2 linked by adjacencies, and then you just replace these adjacencies by another matching of these 4 nodes. Okay, so we have 2 options. If you have A, B, and C, D, you have 2 options for a double swap. You can link AC and BD or AD and BC. Okay, and the interesting thing is that the rank distance corresponds exactly to the weighted minimum operation distance, considering cuts and joins with weight 1 and double swaps with weight 2. That will give you exactly the rank distance computed with the matrices. All right, so given that background, our goal in this paper was to examine the following question. Can we always find the genome exactly in the middle between A and B for any 2 given genomes, A and B? So this is the same as saying that there is a genome attaining the lower bound for this maximum of DAC and DBC. Okay, the lower bound is the distance of AB divided by 2, rounded above, because if you have an odd number, it cannot be equal. All right, so the question is, can we always find that with the rank distance? And the answer is no. Okay, here we have a simple example with small genomes, with only 2 genes, circular genomes, where the rank distance is 2, as you can see by the calculation there. But if you try to find a genome at distance 1 from both A and B, that's going to be impossible, okay? Think about the following way. If you depart from A and you have a step of weight 1, there's only one thing you can do, a cut. You cannot do joins because all the extremities are taken, but you can do cuts. You can do 2 cuts. And these 2 cuts leads to the genome in the yellow square there. But none of these genomes is at distance 1 from B. Actually, I believe they are distance 3 from B. So by just analyzing the few simple cases that arise here, you conclude that there's no way to achieve a center score of 1 in this case. All right. So if it's not possible to achieve that in general, in which cases can we find a genome in the middle? That's our next question. And okay, to answer this question, we'll investigate 2 different cases: cotailed genomes and not cotailed genomes. Cotailed genomes are genomes that have exactly the same free ends, the same telomeres, okay? So in this example here, A and B are cotailed because none of them has any free ends. C and D are also cotailed because they have the free ends A and F. Now, I don't know how many chromosomes they have or what the chromosomes are, but I do know that the free ends are A and F. Well, looking at it this way, I know they have 1 linear chromosome each because only linear chromosomes yield free ends, and each linear chromosome yields 2 free ends. So here we have 1 linear chromosome in C and 1 linear chromosome in D. But I don't know how many circular chromosomes they have, unless, of course, I draw the picture. But they are, actually, I think they are one linear chromosome each, because the dotted lines here must be the adjacencies. Yes, okay. So 1 linear chromosome each. But A and C are not cotailed. A and D are not cotailed. B and C or B and D are not cotailed. All right. So this is the idea of cotailed genomes. All right. So let's start studying with the cotailed genomes. Well, it turns out that if you think about cotailed genomes and the operations that we study here, cut, join, and double swap, every optimal path between 2 cotailed genomes involves only double swaps. This has been proved earlier by Chindelevich and colleagues in 2018, and that's going to be useful in our analysis here. So what happens in the cotailed case? Well, your distance has to be even because you can only use double swaps. Double swaps have weight 2, so the distance is even. So you can think about distance 0, 2, 4, 6, 8, etc. And you see that in each case, you have a number of intermediate genomes. All intermediate genomes have to be at distance 2 from the neighbors in the path. So you can see that sometimes it's impossible to achieve the lower bound. We already saw an example when the distance is 2, but when the distance is 6, it's also impossible because all the intermediates you're going to have will be at distance 2 from A and 4 from B, or 2 from B and 4 from A, and so on and so forth. So in this case, you have to be content with the lower bound plus 1 solution. You cannot reach the lower bound. All right. So summarizing what you just said, if the distance of AB is a multiple of 4, you can have a genome right in the middle. But if the distance is not a multiple of 4, you have to use one extra operation. Your distance, your maximum distance will be 1 more than the lower bound. There's no way to avoid that. Okay. Now let's take a look at the not cotailed case. In this case, the genomes differ by at least 1 telomere. Actually, by at least 2. So in this case, for each number between 0 and the distance of AB, there is a genome that is at distance I from A and distance AB minus I from B. So for any given value between 0 and distance of AB, you can find a genome G with which is in an optimal path between A and B, but also has distance exactly I from A. So then you can always find a center genome that reaches the lower bound because you can find for any value, intermediate value. All right. And this is a brief sketch of the proof. I don't know, I don't want to tire you guys too much, but it's a proof by induction. And I just want to give you the main idea. Okay, so in a proof by induction, the idea is that you have a case A and B, and if you think about any sorting scenario from A to B, and think about the first operation. If the first operation is an operation that leads to a genome that's not cotailed with B, then, okay, you can apply the induction hypothesis and you are done. The problem is that if you apply an operation that leads to a cotailed genome with B, a genome cotailed with B, well, what to do in this case? Well, if this genome is cotailed with B, you know that from then on, you only have double swaps. And there is a theorem that says that you can swap a double swap with a cut. Do them in reverse order. Instead of doing cut and swap, you can do swap and cut with the same final result. So then you are back to the case where the first step doesn't lead to a cotailed genome, and you can apply the induction hypothesis as well. And if you have a join, the same reasoning apply. You can swap, a double swap with a join. All right, so to summarize our results for the center genome with the rank distance. For the cotailed case, if the distance is a multiple of 4, you can reach the lower bound. Otherwise, you cannot. And if they're not cotailed, you can always reach the lower bound. All right, guys. I guess this is all I had to say to you today. I thank you very much for your patience and your attendance. And I'll give the word back to the organizers. Thank you.
Thank you, João. It's always an honor to host a session in which you're presenting a paper. It's a very nice paper, and it's out-of-the-box thinking, using the rank distances to analyze the center genome. Yeah, I really like this paper. So we're opening now for the audience questions. Does anybody have a question or a comment? If you do so, please write your question in the chat or raise your hand. So João, you mentioned that in phylogenetic trees, you have to deal with the case that and which is almost always what happens, that the two or more organisms, they don't have the same genes. So, and you also mentioned in the paper that you're considering applying that approach to genomes with unequal gene content. So, do you have any idea how you deal with deletions, insertions, or substitutions with that approach?
Yes, we have analyzed the question of insertions and deletions in this rank distance scenario, okay? And of course, the first problem is that when you transform the genomes into matrices, they don't have even the same dimension for you to be able to subtract and compute the rank. Okay, we have thought of a number of ways to extend this definition to remedy this situation. We have a paper on that was published in a conference last year, and we are augmenting it and preparing to send to a journal this year. And in this paper, we analyzed the question and came up with two natural solutions for it, okay? But one natural solution is you have to consider, the solution I like most, you have to consider things like semi-genes or semi-chromosomes, which is something that biologically doesn't make sense right now with our current knowledge of biology. But, you know, science is always about exploring frontiers. So a semi-gene or a semi-chromosome will be something like a chromosome with the beginning, with an extremity in the beginning, but no extremity in the end. Now, what does that mean? We don't exactly know. Mathematically, you can think of that. If you put the matrix without an extremity, there is a way to solve that mathematically. But what does it mean biologically? I don't know. Maybe, I don't know. Maybe an extremity that links to two things. I don't know. We have to think about a biological interpretation for that. So that's the problem with this one extension. The other extension doesn't have this problem, but then we have some weird operations that we have to consider in order for it to work. So that's the position we are right now. To extend this to indels, we either have to consider something funny biologically or some weird operations.
Yeah, that approach looks, at least with what we know right now, it looks unnatural, but it's, well, maybe, yeah, maybe we're just missing a part of the puzzle. If we just hope that maybe biology catches up with that. Okay, do you have any other questions? I don't think so. So thank you again, João, for presenting your work in BSB. It's always very nice to have you here with us at the Brazilian Symposium on Bioinformatics. And yeah, I hope you come again next year. And I hope we all can be together, not virtually, but in the same room to discuss our ideas together. Thank you very much.
All right, thank you, Rodrigo, for your kind words. I'll stop sharing now, okay?
All right. So we're 2 minutes early for our next presentation. So Leodécio, are you already in the room?
Yes.
Sorry, I cannot hear you well.
Oh, you can hear me?
No, I think your microphone is storing your voice. Yeah, can you use another microphone?
Sorry.
Leodécio, I just think your microphone is too loud. Maybe you can adjust the volume and could you try
Okay.
this?
Just a minute.
Oh,
it's better.
now it's okay.
Okay.
Yes.
Sorry.
Okay, are you ready?
Okay, I will share my screen now.
So, and now for something different, I'm gonna move away from the subject of genome rearrangements and distances, and see a paper on the classification of medical images with Leodécio. Braz is going to present us this work along with Vinicius Teixeira, Helio Pedrini, and Zanoni Diaz on their I don't know if I'm reading it correctly, IMTNet, is it right?
IMTNet.
IMTNet. So, which is an image text classification network for abnormality detection and automatic reporting on musculoskeletal radiographs. So, Leodécio, you now have the word.
Okay. As the host said, my name is Leodécio Braz, and our work is this title, and we're gonna start now. So, musculoskeletal disorders represent a major health problem that affects a large part of the population. And the X-ray images are one of the most commonly accessible radiological examinations used to detect and locate abnormalities in radiography studies. The process of interpreting image examinations is a typically complex task, and specialist doctors are usually responsible for conducting the interpretation of this type of information. Determining whether a radiography study is normal or abnormal is a challenge problem, because if a study is interpreted as normal, the possibility of disease is excluded, which may eliminate the need for the patient to undergo other tests or procedures. And to assist in the diagnosis process, many automated computational methods, such as computer-aided diagnosis, CAD, have been explored. And recently, transformers have shown success in labeling radiological images. And recent advances in deep learning architectures have improved the performance of CAD systems, which support health experts. Here is some examples of radiography images with a corresponding heat map generated by a CNN, which helps to identify, detect, and locate an abnormality present on the radiography exam. In this work, we proposed an image text classification network for the automatic detection and notification of fractures on musculoskeletal radiographies. Our method uses information extracted from images and artificially generated captions to obtain a classification label. So, initially, we use a caption generator model to create textual data for a dataset without text information. Then, we use a DenseNet 169 and BERT model to create text to perform image and text classification tasks respectively. At least, we use a fusion model that receives a concatenation of feature vectors extracted from both networks. Our main contributions are summarized as follows. The proposed method is applied with a clinical objective for diagnostic abnormality recognition. Distinct classifiers based on deep learning are trained with radiographies and texts for abnormality classification. And experimental results on Mura dataset show that the combination of image and text features can increase the classification results. Deep learning methods are the state of the art for, for classifications tests in medical domain. Many natural language, while deep convolutional neural networks, the DCNNs, are widely used mainly for image domain, many natural language process, NLP, methods have been developed to extract structured labels from free text medical reports. Wang and others authors proposed the CHATS X-ray 14 dataset. They explored the use of some pre-trained DCNN models on ImageNet. And the authors aimed to perform a multi-label classification of thoracic disease and proposed a technique for pathology localization and classification by generating the pathology heat map. Also, Rajipuka and others authors proposed the musculoskeletal radiography dataset, the MURA dataset. We're going to talk later. And they explored the use of this DenseNet 169 to perform a binary classification. Shen and others proposed the dual ShaxNet, which consists of a dual asymmetric feature learning network. And they explored the cooperation between the two distinct and asymmetric networks to learn in a complementary way. And Smith and others proposed the ShaxBERT for radiology report labeling, and they connect the existing reports labeler with range annotations to obtain accurate results, and used a BERT module to obtain the state-of-the-art results for reporting labeling on the CHATS X-ray dataset. At least Pelka and others authors proposed an approach to combine automatically generated keywords with radiographies. And they presented a method to allow multimodal image representation by fusing textual information, putting it on the radiography images, and performing body part and abnormality recognition. So our work is closely related to approaches that explore the use of DCNNs on medical images with the aim of extracting relevant information, as well as approach that explore textual medical information and the combination of both. So our approach explores the cooperation between image and text network to learn the classification of abnormalities in a complementary and accurate way. Our proposed method. Since text representations are not available on MURA dataset, a dataset we're going to talk early, we use a caption generator module to automatically generate medical reports for its image. The caption generator consists on an encoder-decoder framework where the encoder is a HasNet 152 pre-trained on ImageNet. And the decoder is a long short-term memory, an LSTM network, which receives as input the feature vector from the encoder and produces the image caption as output. We train the caption generator model on the radiology object in context, the HOCO dataset, where all images have a corresponding caption information. Here is some examples of original images on MURA and the caption generated after this task. So one example is the first one, where we have an image from the shoulder set which the actual label is normal, and the generated caption by the encoder-decoder is the right shoulder is normal. And another example is the last one, where we have an image from humerus set, where the actual label is abnormal, and the generated caption is X-ray showing the fracture on the right humerus. But not even all the captions generated are good captions. We're gonna talk about this later. But we can see an example on the second image, where the caption generator, is an image from the wrist set, which the actual label is normal, but the generated captions presents no relevant semantic information, whereas X-ray showing of the right wrist. So the intuition behind our proposed method is that the combination of visual and text information will benefit the classification task, improving its results. So for all proposed method, we applied 3 steps. The image classification level, we call it ICL, the text classification level, called TCL, and a fusion classification level called FCL. On image classification level, we trained a DCNN model called DenseNet 169, and we added in this model an attention model called class activation mapping, a CAM, which is employed to indicate discriminative regions detected by the DCNN model, which help to identify the correct class. At the end of this model, we also use this model as a feature extractor. So on text classification level, we proposed a natural language process, an NLP approach, to extract structured labels from artificially generated image captions. So we fine-tuned the BERT model to perform a text classification. We tokenized its image caption text, and the maximum number of tokens in its input sequence was limited to 64. And at the end, we also used this model as a feature extraction. At least on fusion classifier level, the output features from ICL and from TCL models are concatenated into a single feature vector used as input to the fusion classifier, which consists of 3 dense layers. The overall illustration of our methodology. Upper side, we have the caption generator for create captions for a dataset lacking text information. And we have the original image on Mura dataset that we pass this image for the image classification level, which consists of a DenseNet model. And then we also use the image on Mura to generate artificial captions. And we pass these generated captions for the classification on BERT model. And at least we use the features extracted from BERT and from DenseNet, concatenate these features and use for the fusion classifier level. The dataset we conducted our experiment is the musculoskeletal radiographies Mura dataset, which is a large dataset of bone X-rays. The Mura dataset consists of musculoskeletal studies of the upper extremity of the body, and each study contains a multi-view radiography image. Here is some examples of the 7 standard upper extremities present on Mura, upper extremities from the body. The upper extremities present are wrist, wrist, shoulder, humerus, elbow, finger, hand, and forearm. All radiography is labeled as normal or abnormal. Our proposed model takes one or more views for a study case as input. And in each view, our model or method predicts the probability of abnormality. To assess the effectiveness of the entire proposed method, we compare the results of the image, image, text, and fusion classifier level individual. And also, we compare the proposed IMT-net architecture, which performs a majority vote of labels of the three aforementioned classifiers. For elbow and wrist studies, the performance of IMT-net is lower than the fusion classifier individually. For finger studies, the performance of IMT-net is comparable to the fusion performance, which presents the best results. And the performance of IMT-net presents the best results for shoulder, humerus, and forearm studies. In this latter, in particular, our method provides the greatest gain compared to the DenseNet 169 model. For hand study, the BERT model presents a negative kappa, indicating there is no agreement on its results. And the performance of IMT-net is comparable to the performance of DenseNet 169 individual, with no relevant gain. And the fusion classifier individual present the best results for hands study. The results of the BERT model, as expected due to the caption format, show the worst results in all studies. And in average, our IMT-net model presented the best kappa value with a value of 69.20%. Compared to the baseline results of the DenseNet 169, the proposed method presented an overall performance gain, even with artificially generated text data where most contain text with poor quality or lacking relevant information. So, in general, our model was able to extract and combine discriminative features from each proposed branch, the ICL and TCL. We also evaluated our proposed IMT-net and compare with another existing method for musculoskeletal abnormality classification on Mura dataset. In this table, the visual column is related to the image classification task, the text column is related to the text classification task, whereas the last column is related to the proposed method. And compared to this baseline of another work, our proposed method yields a high performance for musculoskeletal abnormality classification on Mura dataset. Here, we analyzed specific examples from the test set and the predictions on each level. Here, we have the original image. We have the generated hatch map by the class activation map, the CAN, on the DenseNet 169, and the associated generated caption and the predictions and actual class, and some reason that we had for each example. In the first two examples, all levels were able to correctly label the input image and text. The BERT model correctly detected relevant information and was able to discard spurious information present in both captions. The DenseNet 169 model could also identify relevant regions on the image. On third example, which contains poor textual information, in the third example, the generated caption was D of D, D of D, D of D. So With absolutely no semantic information, the BERT model incorrectly predicts this example, while DenseNet 169 correctly predict with a high confidence. It's also possible to observe a well-defined highlighted area on heat map of the radiography that was most important for their model make the prediction. And in the last example, while DenseNet 169 was unable to detect the presence of abnormality in the image, the BERT model was able to distinguish relevant information from the caption and correctly label the abnormality as positive. All features and predictions performed by the DenseNet and BERT model were considered in the fusion level classifier, which could increase the classification result. So as conclusions, we proposed an automatic caption generator for musculoskeletal radiography image and a method for automatically combining these artificially generated captions with radiographies for accurate musculoskeletal abnormality classification. We also presented a data fusion approach method, and we archived competitive results. And as future works, we intend to explore other fusion methods to combine features from different heterogeneous modalities. We would like to thank Institute of Computing, Unicamp, FAPESP, CNPq, CAPES, and NVIDIA. And this was our work. Thank you for your attention.
Thank you very much, Leodécio. We're now open for questions and comments from the audience. So please post your messages on the chat or raise your hands. So to draw attention to you. So Leodécio, you mentioned you use the ROCO data set to train a caption generator for the to generate captions for the images in the mirror data set. But yeah, the ROCO data set doesn't only contain X-ray images. It's all of the many varieties of medical imaging. And if I understood correctly, the mirror data set only has X-ray images, right?
Yeah. ROCO dataset have a range gamma of the radiology image, while Mura don't just have X-ray images.
You use the whole data set to generate the classifier?
Well, dataset ROCO or Mura?
The ROCO, yeah, the ROCO.
Yeah, we use all radiology images on the ROCO, because ROCO also have another class that is not radiology. We use just the radiology for train an encoded decoder to generate image from Mura, text from.
Sorry. So that includes X-ray, CAT scans, MRIs, etc.
Yes. We did not separate just the X-rays on ROCO. We use all radiology images.
Yeah, but the thing is, the CAT scans, X-rays, and MRIs are completely different. You also said use. Did you also use the ultrasound images?
Sorry, I did not understand.
Did you also use the sonograms, the ultrasound images?
I think the audio is not.
Did you also use the ultrasound images?
Yeah, yes. Also ultrasounds and computer tomographies is present on ROCO. It also uses it.
So there are the kind of image each method produces is completely different from the X-rays. So did you try to do something like a style transfer to, I don't know if it would improve the results or make it worse, but maybe you could use a style transfer to.
We would to believe that our model was capable to generalize or adapt to the Mura captions, but we saw that that was not true, because the huge of the caption generated was not with a good quality for the classification. So this is the main one of the main problems of the work, that the data used for train the caption generated was not closely with the data of the Mura. And for this, the generated captions presented no good quality. For we can see by the results of the batch that is a poor results.
Yeah, it's interesting that the caption generator it tends to only look at the right part of the body. So I don't know if you have any more examples, but of all of the examples in the paper, it's always right shoulder, right wrist, right hand, right humerus. Even when it's at the left, it's clearly the left hand. So it's that's curious.
Yeah.
I mean, yeah, it looks like the classifier is right-handed. The caption generator is right-handed. So, do you have any idea why that's the case?
Probably the captions present on Roku when was an X-ray image contains the body part information. So when the encoder decoder saw see X-ray, they learned to identify some body part and prediction this as the caption.
Yeah, so it looks like the data set is skewed to the right part of the body. At least the Roku data set.
Yeah.
And maybe you could consider using some sort of style transfer on the images that are not X-rays to. I mean, you'd have a neural net that's merely gonna hallucinate how would like an ultrasound look if it were taken as an X-ray, but maybe that could improve the accuracy or the quality of the captions generated. So yeah, I don't know. That's just one suggestion.
Yeah.
Or maybe it's
On the text we say that the main problem of the work is just the caption generator. On the main problem is the caption generator, and we also are observing as a future work and others ways to try to generate good captions for these examples. So as you said, transfer style can be used. Style transfer.
Yeah. All right. Do you have any more questions? Anyone else? Yeah, Yaris is quite quiet today, or it's Zoom. So thank you again, Leodécio, for your wonderful presentation. And do you have any updates on the next paper?
Yes. Hello, everyone. My name is Valdeir. Well, despite our efforts, the next presenters still having problems to get in this session, and they also do not provide backup. So we are looking to reschedule this last presentation in another session. So this session will end right now. But before that, I just would like to make 2 announcements. We're gonna be back here 2 p.m. for the invited speaker Baz Dutil speech. And this one will be not live streamed on YouTube. It is a exception because the speaker do not authorize. And after that, at 4 p.m., we're gonna have the steering committee meeting, which is a meeting to discuss the event and to discuss the next edition of this event. And it is an open meeting for everyone. This one will be in Portuguese. And all of you are invited to join us and discuss the preparation for the next Brazilian Symposium on Bioinformatics. So I would like to thank you everyone here for your participation, and I have a special thanks for Rodrigo for chairing this session. And as I said, we are looking for reschedule the last presentation in another session, and we're gonna have this 2 more session today. An invited speaker, Bas Dutil, and then the meeting steering in the afternoon. Thank you very much for coming here.
Thank you, Valdir. And I'd like to thank the organizers for inviting me to host this session. And on behalf of the organizers, I'd also like to thank the presenters and the authors that have brought us their work today. It's the high quality papers, the top-notch work. It's thank you, Klairton, Lima, Pedro, Olímpio, João, Meidanis, Leodécio, Braz, and the other authors. And I hope you consider submitting your papers again next year for the next year's Brazilian Symposium Bioinformatics. So let's have a break and have a virtual coffee.